Just to give you a background, I actually come from a very software background, and I ended up in simulation by accident. But to answer the previous presenter's question, whether you can do the line of road and terminal interaction in one model, you can. I've actually have done it for a big railroad company in Australia called Horizon. And yeah, actually, I should probably talk to you afterwards. And I'm doing another project for a mining company that happens to own like the rail, the track, the terminals as well. So yes, it's possible, and AnyLogic is actually uniquely suited to that because it allows you to mix a lot of different approaches to modeling. Anyway, so today though, I'm going to talk about public transportation and specifically focus on customer on public transportation. So, you know, I'm from Australia. I don't know if anybody here is from. Hello. I was just gonna say it's very far, so people probably don't know what's going on down there. But essentially, a similar situation to what the previous presenter was talking about. There's some capacity issues across all metropolitan areas in public transportation. So we're talking all the major cities. The Australian government has announced that they're going to spend a lot of money in infrastructure development. So there's a lot of conversations about how to best allocate that money. And what's more important regarding what happened in the last approximately 8 to 10 years is that the way that the customer information on public transport is being collected has changed as well. So previously, there were conventional methods of collection such as manual surveys or looking at CCTV footage or look at the weight of the train to see how many people are on it. But these days, we have smart cards. And smart cards are now across the whole country in all the major transportation hubs. And they've been used by a lot of customers. And I think Perth was the first one that went ahead with it and had an integrated. So this cards cover movement of passengers not just on one mode of transportation, but actually intermodal. So we're capturing buses, trains, ferries, light rail, things like that. So now we actually have very high fidelity of passenger movement through the network, the time it takes for them to do that, how much it costs them, those types of factors. So that was a major enabler for this work because what we're trying to do is we're trying to have a customer-centric view of infrastructure. Okay, so what we want to be able to do is to be able to tell the customer when something happens, we can basically tell them, well, how long they're going to be delayed. Maybe they should make another choice. So there's a lot of apps that are being rolled out on mobile devices. We also want to tell the operators of the networks about, well, this is what the customers are doing. This is what they're going to be doing next month or next year. We also want to be able to inform the future planners regarding whether they should invest capital in doing things like that. But essentially, it all comes down to the person's trying to get from A to B. This is the time that it should take them. If we can do it better, we should. But if we can't, we should really make sure that if anything bad happens, so like a derailment or a breakdown or a medical emergency, the number of people and the duration by which they're actually delayed is minimized. So to do that, we're going to actually pick a metric. So we have identified lost customer minutes as a metric. And so it's kind of like the definition there is very broad. And of course, the major problem with the way of stating it like that is essentially if you delay 1,000 people by 1 minute, that's not so bad. But if you delay 100 people by 10 minutes, that's actually kind of worse, although the values are the same. So what you want to do is you want to actually not just count the minutes, but give them some context. Basically see what the people were doing, if it was during peak time, if it was during the day, if the person was going to work, or if they were just traveling for leisure. The value of time at different situations is different, so that has to be all augmented. And some of the context actually comes from the utilities, where they look at, for example, if you lose a kilowatt hour in a business center, you are actually impeding economic activity. And if you lose a kilowatt hour, in a suburban area, that's not good either, but it's not as bad. Although you just lost a kilowatt over a space of an hour. So with that said, what we did is we actually built a network model. And we used, so to your question regarding I'll talk about it later. So firstly, I'm going to talk about why we picked AnyLogic. So the existing tools that the previous presenter shown and some others that our clients are using, they're not actually customer-oriented, they're train-oriented. The train is a proxy for what's on the train. And that's actually not very good when you're looking to extend the work further to cover the choices the customer makes about whether they're going to catch a train, which train they're going to catch, whether they maybe take a bus or take a ferry, or maybe they'll change modes midway. And that actually goes back to the situation that the customers are not really represented as agents, as people with agency, as some entity that's trying to achieve something. And the other big thing is that, well, why would you even care? Like, you can just look at the timetable and look at the train, but the reality of it is the systems have been evolving and are continuously evolving to answer the customer's needs. And that's where the revenue is coming from, that's where the people's opinion of the service comes from. And you really have to start making decisions and models that actually address those concerns. And AnyLogic is actually really excellent at that, because it allows you to mix the existing engineering knowledge represented using discrete event paradigm and the kind of new wave of knowledge, which is the customer behavior and customer choices. But what's more important is that if you want to extend it, if you want to have new types of customers, or if you want to have new types of trains, you can actually do it with relative ease. I mean, it's a few days of work, depending on the complexity, once you've actually established the base network model, to start running different types of trains on it. And that's something that other tools don't do so well, scalability. So this is an example of RailSEE, and that's a major output of RailSEE. It's a great system, a great tool. So you give it a whole bunch of engineering information, you give it a timetable, and it gives you this, which is it's a train graph. So essentially, it will tell you if, given your engineering information and your current network, you can meet the timetable obligation. There's no representation of what the customer thinks about the whole experience. So, with that in mind, we set out to actually build a network model that includes all that information. And it turned out to be quite a task from the data point of view. The biggest one was the network layout, as you've mentioned, because essentially it was all in bits of GIS information all over the place. And obviously, AnyLogic requires it to be specific drawn lines on the canvas. So we actually wrote an algorithm that parses the GIS information and draws the lines in AnyLogic. And we actually had to synthesize, because parts of the network were very readily available from the clients and parts not so available, because they were still in the process of mapping some of the things out. So surprisingly, we actually went to the OpenStreetMap. And you know how previously it was mentioned that it's like a Wikipedia for maps. So there was a guy who actually worked for our client, and he was an enthusiast, and he was a train driver. And he carried a tag on himself every time he drove a train. So, and then he recorded all the information and put it online. And so we got it all out of that. And we actually went to our client and said, look at what's available publicly. And they were quite surprised. But yeah, so it was very helpful. I don't know what the guy's name is. I just know his username. But thanks to him. So the other things that we got, obviously, we had to get the train data. So, the network is fairly old, and there's different types of trains running on it, and they have different characteristics, obviously. We had to get the timetables. The timetables change day to day. depending on special events or whether it's holidays or not. Very important, we had to get the operating rules. So there's some rules surrounding the way that the network's managed. Different parts of the networks are managed because of the way that the capacity is assumed. So certain trains are given priority in certain situations. Very important also, we had to get incident data. So we had to, luckily our client actually had a fairly good incident tracking system. And it was actually quite interesting because what was important in that data set wasn't just that, well, this train got delayed by 10 minutes or something. What was important is that you could actually see that this delay caused this delay, caused this delay, and you could see the propagation throughout the day, and you could see the network recovering. So if the delay was in the peak hour in the morning, it would be recovering, for example, for 3 hours or for 4 hours until the people can actually, until the whole thing is running on time again. And finally, it was the passenger data, which is the smart cards that I talked about earlier. And there's also, so we also got access to the surveys that were collected using the old methods as well. One of the things that we had to do is, so this is, we were using Rail library in the background over the network that we built from the GIS. But we had to write our own train move to component, which you'll probably have to go through at some point as well. And that was mostly to make sure that the safety rules of the network are observed every time the train is moved. So that's kind of, that's just to show that that's part of the AnyLogic that we found very useful, is that you can actually componentize bits of logic and then repeat them in different parts of the model. And AnyLogic just supports it very easily. In other tools that I've used, it's actually quite a task to get that working out of the box. So back to the lost customer minutes. So that's actually, there's different ways to calculate it, but here's just a very quick example to show that there are some situations where the train is late, but the customer still arrives on time, so no minutes lost. There are some situations where obviously the train's late and yep, there's some minutes lost. And there are some situations where the train's late, but although it's late, it traverses the segment within the time allotted to it. So that, and the customer, especially in suburban networks, there are some times where the trains are running like every 3 minutes, every 2 minutes. So the customer doesn't actually care if that specific train is 10 minutes late. They just show up to the station and their travel time is just as expected. So in that case, you don't actually have any lost minutes. Although, as I will show later, other methods of calculating this metric actually say, well, no, that's actually really bad. So this is kind of what the model output looks like. The map, kind of disregarded the map, I just threw something in there. We actually have the map live, full live, so we have the map in the background for when the trains are running. At the top, you have the numbers of customers waiting at each station, and at the bottom, you have the train graph that is the simulate. So you have the red color, which is the actual movements, and you have the blue color, which is the scheduled movements. I don't know how many of you are familiar with train graphs. I know there's some people, yeah, there's a few. So on the y-axis, you have the actual stations, and on the x-axis, you have time. And as the train moves through the network, you have basically this sloped line that shows where the train is at different times. So what are the outputs? Okay, let's look at the outputs. Well, that's the train graph. So here's an example of a train graph where something went wrong. So you have the blue line where there was scheduled movement, dwell time, then return movement, another dwell time, then return movement. So it's kind of like backwards and forwards. And then the red line actually shows you that the train was moving towards its first destination, got delayed for a while, set somewhere, then it was given a green light, it went to its destination finally, returned, spent very little time dwelling in both locations, and then from that point onwards runs on time again. So the client found that type of output very important because that's kind of a conventional way of representing train movement in a network, and it was very easy, it was kind of very familiar to them, it was very advantageous. This is kind of a very busy graph, but it allows us to show multiple things on the same graph. It allows us to show when the incident actually took place. So if somebody had a heart attack, the train gets stopped, and that's a delay. Delay starts. Then the ambulance arrives. People take care of the person, take them off the train. The incident is over. So the incident has stopped occurring, but the delay is ongoing. So you have another graph there, which is the total number of trains affected. So because of that one delay, and it's a network system, the buffers fill up, so you have to push traffic, slow traffic down. And as a result, you actually still incur in lost customer minutes, even though your incident is technically over. And that was a way to show basically, well, this is what actually happened, this is the ongoing delay, and this is the recovery, and this is the impact. And that's kind of what it looks like when you actually run it in the model. So the model allows you to put little incidents in there, and it will actually simulate them. It will actually say, well, this train got stopped. But it only does the first point, the first train. The rest of it is behavior of the network according to the operating rules that have been specified by the client. So for example, the replay that was shown previously, they're actually records of where the trains were. We only recorded first train. The rest of it was actually just a simulation saying, well, if you have a problem here, then that's how your queue is going to form. And as a result, you see on the train graph at the bottom, there's this flat bit in the middle. That's basically the train that got stopped somewhere. And as a result, there's actually 3 lines there that have flat lines, which is essentially the 3 trains that were affected. Why is it so? I mean, again, it's a very busy graph, but what it allows you to do is it allows you to very quickly compare scenarios. So the major thing about this was, look, if we have incidents and we have to deal with them, we have to basically find a way to very quickly show that this strategy is better than that strategy. If you have trained medical staff at certain locations, for example, they can minimize some incidents before the arrival of officials in an ambulance or something like that. And yeah, that costs money, but if along a certain line you have 15 incidents a week, then maybe it's worth the money. And you can do it, you can just show like, well, if we take the historical information, replay it, and that's kind of what the graphs look like. The other thing that was actually quite advantageous was to show, well, how many people are actually at each station. So I don't know if you can see very well, but there's actual numbers above each bar, just to show, well, this station is popular at this time, this station is popular at that time. And then basically to show you how the actual peak of usage moves through the network. So the further away you are from the business center, the earlier your peak starts, and the earlier it ends as well. And it's very easy, in this way, it's actually very easy to show the outputs and say, well, in some places the peak starts at 8:30, in other places it starts at like 9. The other thing it shows is that, so the graph at the bottom, it shows the number of people on each train. So that if the train has to be stopped, if there's a derailment, if there's some kind of issue, and you need to order buses or alternative forms of transportation, or you need to estimate how much money you have to return to people for their tickets, that's basically the way to figure it out. And so going back to actually talking about the individual trains, so a very big thing about customer experience is crowding. And you have, part of the question that the client posed to us is they want to actually be able to tell that if we look at individual trains going through parts of the network, can we actually tell how good is it for people on the train? Like how many of them are sitting down, for example. And we tried to find kind of a way by looking at the actual smart card information and then, well, kind of synthesizing people's origin and destination demand on real-time basis, and then generating agents out of that information and injecting them into the model. So a little guy shows up, and this little guy is the representation of, say, 2 or 3 people that took a train on certain days, and he says, I want to go to another station, what am I going to do? And then the train arrives and goes, well, this train goes to where I want to go, so it pops on the train. And over time, we aggregate that information. So this is kind of a station view as well. So this is just to show that we've really leveraged the AnyLogic dashboard capability quite a lot. Having that to go with modeling was very advantageous. So what we ended up is this graph. So this graph shows 3 ways to calculate lost customer minutes. The top one is the timetable deviation. The bottom one is what's called the mean headline calculation. And they're both train-oriented. And you can see that one of them is, takes the worst case scenario. It's very bad, makes the outputs look kind of bad. And the other one, it's actually originally implemented by London Underground. And London Underground, all the trains are very close together. So you end up, that is the context in which that type of metric is very useful. On big networks that include like long distances and short distances, and trains run like 2-3 minutes or 15 minutes apart, you actually, it starts lying a little bit. It starts underestimating the lost time. And the middle one is the one where you actually look at the agents, the specific agent travel time. And that actually gives you, it shows that, well, that's probably what's actually happened. And, well, how's it useful? Well, that's kind of, this is the many ways that metric can be used, but the essential word is how do you measure your performance? And if you have that metric, agreed among many different groups within the company, so operational, maintenance, investment, customer service, they all talk in the same language, and having that as a part of the conversation is a really, really advantageous thing to have in a big company. And in the future work, so we are working on extending it into other forms of transportation. We are trying to get the customers to behave like pedestrians. So we're looking at platform crowding and egress. And finally, we're looking at future development of the network. So we're talking about lighter trains, automated trains, different signaling systems, different communication systems. So yeah, it's been a great experience. Thank you.
Questions? Anybody? Okay, great.
Thanks.
All right. Thank you.